Before the steam engine, nearly all mechanical work depended on natural or biological sources of energy. Humans, horses, oxen, windmills, and water wheels provided the power needed for farming, mining, and early manufacturing. These systems had supported societies for centuries, but they imposed strict limits on how much work could be done and where it could be done. Human and animal muscles could only deliver small amounts of energy for short periods. Animals required food, rest, and care, and their strength could not be increased beyond natural limits. Wind and water offered stronger power, but they were unreliable. Water wheels worked only where rivers flowed with sufficient force, and windmills depended entirely on weather. If the wind was weak or a river froze, production stopped. Mining exposed these weaknesses most clearly. As coal and metal mines grew deeper, groundwater flooded the tunnels. Removing this water with buckets or horse-driven pumps was slow and costly. Many mines could not be worked efficiently because water accumulated faster than it could be removed. Valuable resources remained underground simply because there was no reliable way to drain them. Manufacturing faced similar constraints. Mills were built next to rivers, not because rivers were ideal locations, but because water was the only dependable source of mechanical motion. This limited where factories could be placed and how large they could become. Production depended on geography rather than demand. By the early 18th century, Europe's population and economy were expanding. More coal was needed for heating and industry. More goods were needed for growing cities. Yet the methods of producing power had changed very little. The problem was not a lack of labor or raw materials, but a lack of controllable energy. Industry needed a source of power that could operate continuously, in any location, and at increasing scales. This gap between economic growth and available power created the conditions for a new technology to emerge. The early Industrial Revolution intensified the demand for power. Textile production expanded, ironworks increased output, and coal mining became essential to fuel furnaces and homes. These activities required mechanical motion, spinning fibers, lifting ore, and driving tools, but traditional power sources could not keep pace. Coal, in particular, revealed the limits of existing technology. Deeper mines produced more fuel, but also more water. Pumping systems driven by horses or water wheels could not always manage the increasing volume. In many cases, mines had to close because flooding made them unsafe or uneconomical. Factories faced a similar challenge. As machinery improved, it became capable of producing goods faster than ever before. However, this machinery still depended on water wheels or animals. A factory located away from a river had few options for mechanical power. Even rivers varied with seasons, becoming weaker in summer and dangerous in flood conditions. This mismatch created an energy problem. Production methods had advanced, but power generation had not. Industry needed a source of energy that could be created where needed and controlled by human design rather than nature. Early engineers understood that heat could be used to create motion. Steam, produced by boiling water, expanded with force. This expansion could move pistons or lift weights. The idea was simple in theory: convert heat into mechanical work. The difficulty lay in doing this efficiently and safely. The search for reliable mechanical power was driven not by curiosity alone, but by practical necessity. Mine owners, factory operators, and governments all had reasons to support better engines. Energy was becoming the central factor in economic growth. Whoever could provide consistent power would shape the future of industry. Before James Watt, the most important steam engine was developed by Thomas Newcomen in the early 1700s. The Newcomen engine was designed primarily to pump water out of mines. It worked by filling a cylinder with steam and then cooling it with water, causing the steam to condense and create a vacuum. Atmospheric pressure then pushed a piston downward, driving a pump. This design was effective for draining mines, but it had major flaws. Each cycle required the cylinder to be heated with steam and then cooled with water. This repeated heating and cooling wasted enormous amounts of energy. Large quantities of coal were burned just to keep the engine operating. Because of this inefficiency, Newcomen engines were expensive to run. They were practical only in coal-rich regions, where fuel was cheap. Even then, they produced slow and uneven motion. They could pump water but were poorly suited for driving factory machinery. These limitations mattered because industry needed more than pumping. It needed continuous rotary motion to turn wheels and shafts. The Newcomen engine could not easily provide this. It was tied to a narrow purpose and consumed too much fuel to be adapted widely. By the mid-18th century, engineers recognized that steam engines had potential, but they needed improvement. The basic idea of using steam pressure to create motion was sound. The problem lay in how heat was managed. Much of the energy from burning coal was lost instead of being converted into useful work. This inefficiency became the central technical challenge. If steam engines could be made more economical, they could be used not just in mines, but in factories, mills, and transportation. The need was clear: a steam engine that wasted less fuel and delivered smoother power. James Watt's improvements transformed the steam engine from a specialized pump into a general source of mechanical power. By making steam engines more efficient, he reduced fuel consumption and increased reliability. This allowed steam power to move beyond coal mines and into many areas of production. Factories no longer needed to be built beside rivers. Steam engines could operate wherever coal could be delivered. This freed industry from geographical limits and allowed cities to grow around centers of manufacturing. Textile mills, ironworks, and machine shops could now function with consistent power throughout the year. Steam engines also reshaped transportation. They provided the basis for steamships and later for steam locomotives. Goods and people could be moved faster and more predictably than ever before. Trade expanded across regions and continents. The long-term impact of steam power was cumulative. It did not replace all older methods overnight. Instead, it gradually became the standard source of mechanical energy. As engines improved, they grew smaller, stronger, and more adaptable. Entire industries formed around their construction and maintenance. More broadly, steam power altered the structure of work. Production shifted from small workshops to large factories. Labor became more specialized. Output increased dramatically. These changes formed the foundation of modern industrial society. The success of the steam engine was not based on novelty alone. It succeeded because it addressed a central economic problem: the need for controllable, scalable energy. By converting heat into motion with increasing efficiency, steam engines bridged the gap between natural power and mechanical industry. In this way, the steam engine did not simply improve existing systems. It created a new relationship between energy and labor. Mechanical power could now be generated on demand and applied to many tasks. This shift made sustained industrial growth possible and set the stage for later technologies based on the same principle of energy conversion. James Watt was born on January 19, 1736, in the port town of Greenock, Scotland. Greenock was an active center of shipbuilding and trade, connected closely to maritime commerce. Watt's father, also named James Watt, worked as a shipwright, merchant, and contractor for the local town council. His work involved building and repairing ships, making tools, and handling mechanical equipment. This placed young James in an environment where practical craftsmanship and mechanical problem-solving were part of daily life. Watt's mother, Agnes Muirhead, came from an educated family and had strong interests in learning and religion. She encouraged reading and careful thinking at home. From an early age, Watt was surrounded by tools, measuring instruments, and wooden models. Unlike many children of the period, he had access to materials that allowed him to experiment and observe mechanical motion directly. His health in childhood was fragile. Watt often suffered from headaches and stomach illnesses, which limited his ability to attend formal school regularly. As a result, much of his early education took place at home. This gave him freedom to explore subjects at his own pace. He developed strong interests in mathematics, geometry, and natural philosophy, which at the time referred to the study of physical laws. This combination of domestic instruction and exposure to mechanical work shaped Watt's habits. He learned to think carefully about measurement, proportion, and function. His father's workshop taught him how materials behaved when shaped or assembled. His mother's instruction developed his reading and reasoning skills. Together, these influences created a foundation that linked theory with practice, an unusual balance for the period. Rather than being trained solely as a craftsman or purely as a scholar, Watt grew up between these two worlds. He became comfortable working with both books and tools. This early environment did not point directly toward the steam engine, but it prepared him to understand machines not only as objects, but as systems governed by physical principles. As Watt grew older, his interests became more focused on instruments and precise measurement. He learned to make small mechanical devices such as compasses and mathematical tools. These skills required fine hand control and an understanding of angles, distances, and calibration. In his late teens, Watt traveled to London to train formally as a maker of scientific instruments. London was one of the few places where such training was available. There he learned how to produce quadrants, telescopes, and other devices used by navigators and scientists. This work demanded accuracy, patience, and knowledge of geometry. However, Watt's time in London was difficult. He struggled with poor health and limited money. After about a year, he returned to Scotland, unable to complete a traditional apprenticeship. Despite this setback, he retained valuable knowledge about instrument construction and repair. He soon found work at the University of Glasgow, where he was employed as an instrument maker. The university environment exposed him to professors and researchers who studied mathematics, physics, and chemistry. This setting allowed Watt to observe scientific discussions and experiments closely. At the university, Watt repaired and constructed devices for teaching and research. This role required him to understand how instruments functioned and how they represented physical laws. It also placed him near leading thinkers of the Scottish Enlightenment, who valued rational inquiry and practical improvement. Watt's education therefore combined three elements: home instruction, workshop training, and academic exposure. He did not receive a formal engineering degree, which did not yet exist, but he developed a technical literacy that allowed him to analyze machines carefully. He became skilled not only in making tools, but in understanding their efficiency and limitations. This technical background was essential to his later work. When Watt encountered the steam engine, he approached it not as a miner or factory owner, but as someone trained to measure, compare, and improve mechanical performance. Despite his growing skills, Watt's early career was unstable. His work as an instrument maker did not provide steady income. Demand for precision instruments was limited, and competition existed from established craftsmen. Financial uncertainty became a constant concern. In addition, Watt continued to experience health problems. Periods of illness interrupted his work and reduced productivity. These challenges forced him to rely on careful budgeting and occasional support from family and friends. During this period, Watt also attempted to establish himself as a surveyor, a profession that used his mathematical knowledge. He learned land measurement techniques and produced maps. However, this work was seasonal and not always reliable. His employment at the University of Glasgow helped stabilize his position somewhat, but it was not highly paid. He repaired telescopes, thermometers, and experimental equipment for professors. This work brought him into contact with scientific ideas, but it did not yet bring recognition or financial security. Watt's early adulthood was therefore shaped by persistence rather than success. He developed habits of detailed observation and careful record-keeping. Because resources were limited, he learned to reuse materials and improve existing designs rather than create entirely new ones. These experiences influenced how he later approached invention. Instead of attempting radical designs immediately, he focused on modifying and improving known machines. His ability to work under constraint taught him to value efficiency, not only in engines but in his own labor. This period of difficulty was not dramatic, but it was formative. Watt became cautious, methodical, and analytical. These traits were essential when he later examined the steam engine's flaws. In 1764, James Watt married Margaret Miller, a cousin of his business partner. Margaret provided emotional stability and managed household affairs, while Watt continued his technical work. Their marriage allowed him to focus more consistently on experiments and mechanical problems. They had several children together, though only 2 survived into adulthood, reflecting the high child mortality of the period. Family responsibilities added financial pressure, but also reinforced Watt's need for stable income. Margaret's support was significant. She assisted with correspondence and domestic organization, helping Watt maintain focus on his technical pursuits. However, in 1773, she died suddenly after illness. Her death affected Watt deeply and disrupted his work. Several years later, Watt remarried Anne MacGregor, who also provided household stability and support. This second marriage coincided with the period when Watt's steam engine improvements began to bring wider recognition and financial success. Despite his later fame, Watt remained personally reserved. He did not seek public attention and preferred private study and workshop activity. His letters show concern for family life and financial responsibility rather than ambition for status. Watt's personal life illustrates the conditions under which his work developed. His inventions did not emerge from isolation, but from a household that required steady income and practical results. Marriage did not transform him into a visionary figure, but it provided a structure that allowed sustained effort over many years. His domestic situation reinforced the practical character of his engineering work. He was motivated not only by curiosity, but by the need to make machines that could function reliably and attract commercial interest. James Watt's direct involvement with steam engines began in the mid-1760s, while he was working as an instrument maker at the University of Glasgow. The university owned a small model of a Newcomen steam engine, which was used for teaching purposes. When the model stopped working properly, Watt was asked to examine and repair it. As he studied the machine, Watt noticed something important. The engine required a large amount of heat to operate, yet much of that heat seemed to be wasted. In the Newcomen design, steam was admitted into a cylinder and then cooled with water so that it would condense and create a vacuum. This vacuum allowed atmospheric pressure to push the piston downward. While the process worked, it involved heating and cooling the same cylinder repeatedly. Watt measured how much steam was needed to refill the cylinder after each cycle. He discovered that a great deal of steam was required simply to reheat the cold metal cylinder before it could do useful work. In other words, most of the fuel was being used not to move the piston, but to compensate for heat lost during condensation. This observation shifted Watt's attention from general mechanics to the science of heat. He began studying how steam behaved and how much heat was required to change water into vapor. These studies were influenced by contemporary research into latent heat, particularly the work of Joseph Black, a professor at Glasgow. Rather than attempting to redesign the entire engine immediately, Watt focused on understanding the source of its inefficiency. He carried out experiments to determine how quickly heat was absorbed by metal and how steam condensed. His goal was not to increase power, but to reduce waste. This analytical approach was significant. Earlier engineers had focused on making engines larger or stronger. Watt focused on energy loss. His method reflected his background in measurement and scientific instruments. He treated the steam engine as a system whose behavior could be quantified and improved through careful observation. The encounter with the Newcomen engine therefore marked a turning point. Watt moved from general instrument work to the specific problem of steam power. His work began as repair but quickly became investigation. The central question became, how could the engine produce the same motion while consuming less fuel? Watt's most important insight came from this focus on heat loss. He realized that the fundamental problem with the Newcomen engine was that the same cylinder was used for both heating and cooling. If steam could be condensed without cooling the main cylinder, the cylinder could remain hot, and much less steam would be required for each cycle. This idea led to the concept of the separate condenser. Instead of injecting cold water directly into the main cylinder, Watt proposed condensing the steam in a separate chamber connected to the cylinder by a pipe. Steam would leave the hot cylinder and enter the condenser, where it would cool and condense into water. This would create a vacuum that pulled the piston downward, just as in the Newcomen engine, but without cooling the working cylinder. In theory, this arrangement would greatly reduce fuel consumption. The cylinder could remain hot while condensation occurred elsewhere. Watt built experimental models to test the idea. These early versions demonstrated that the principle worked. The engine consumed less steam and therefore less coal. However, turning this concept into a practical machine was difficult. The condenser had to be kept cool, while the cylinder had to remain hot. Pipes and joints had to be sealed tightly to prevent steam leaks. Manufacturing techniques of the time were not very precise, and small flaws could cause significant losses of pressure. Watt also faced financial and technical limits. He did not have the resources to build full-scale engines on his own. Progress was slow, and experiments were repeated many times with small improvements. Despite these obstacles, the separate condenser represented a genuine breakthrough. It did not change the basic principle of steam engines, but changed how heat was managed. The engine no longer wasted most of its energy reheating the cylinder. Instead, energy was used more directly to produce motion. Watt patented this idea in 1769. The patent protected not a single machine, but a method of improving steam engines. This legal protection later became central to his commercial success, as it prevented competitors from copying his design without permission. The separate condenser marked the transition from theoretical improvement to applied invention. It demonstrated that steam engines could be made significantly more efficient. The remaining challenge was to produce engines that could be manufactured reliably and sold to customers. Watt's technical insight alone was not enough to bring steam power into widespread use. He needed financial backing, manufacturing facilities, and business organization. This support came through his partnership with Matthew Boulton, an industrial entrepreneur based in Birmingham. Boulton owned the Soho Manufactory, one of the most advanced industrial workshops in Britain. He recognized the potential value of Watt's engine improvements and offered both capital and production capacity. Their partnership combined Watt's engineering skill with Boulton's business experience. Under this arrangement, Watt focused on refining the engine design, while Boulton managed production, sales, and customer relations. Together, they worked to solve practical problems such as improving cylinder construction and ensuring reliable sealing of joints. These details were essential for the engine to operate efficiently in real conditions. Boulton and Watt also developed a business model based on fuel savings. Instead of selling engines at a fixed price, they charged customers a portion of the coal saved by using Watt's improved engine compared to older designs. This arrangement made the value of the invention measurable and attractive to mine owners and factory operators. Their first engines were installed mainly in mines, where fuel efficiency mattered greatly. Over time, the design was refined to produce smoother and more controlled motion. Additional features, such as the sun and planet gear, allowed rotary motion suitable for driving factory machinery. The partnership also defended Watt's patent rights against competitors. Legal disputes occurred, but the patent system allowed them to maintain control over key improvements. This protection gave them time to establish their engine as the preferred design. The collaboration between Watt and Boulton illustrates how invention required more than technical creativity. It required organization, finance, and production capability. Without this partnership, Watt's ideas might have remained experimental rather than becoming industrial tools. Initially, Watt's engines were used mainly for pumping water out of mines, just like earlier steam engines. However, their improved efficiency made them attractive for broader uses. Boulton and Watt worked to adapt the engine for continuous and controllable motion. One major change was the development of rotary motion. Factory machinery required rotating shafts rather than simple up and down movement. By adding mechanical linkages that converted linear piston motion into circular motion, Watt's engine could drive spinning and weaving machines. This adaptation expanded the engine's role beyond mining. Textile mills, flour mills, and ironworks began to use steam power. Factories could now operate independently of rivers and wind conditions. This increased flexibility in factory location and scale. The spread of steam engines changed the structure of industry. Production became centralized in large facilities where machines worked continuously. Output increased and costs fell. Steam power also encouraged further mechanization, as new machines were designed to take advantage of steady power. By the end of the 18th century, Watt's improved steam engine had become a standard source of industrial energy in Britain. It was not the only engine in use, but it was among the most efficient and adaptable. This transformation shows how Watt's journey moved from observation to general application. His work did not end with a single invention. It continued through adaptation and expansion. The steam engine became a general-purpose machine rather than a specialized tool. Watt's contribution, therefore, lay not only in improving an engine, but in changing its role in society. Steam power became a foundation of industrial production. The engine moved from the mine to the factory, and from a limited function to a universal one. Through this process, the steam engine became a central technology of the Industrial Revolution. It linked scientific understanding of heat with practical machinery, creating a new relationship between energy and work. The steam engine operates on a simple physical principle. When water is heated, it turns into steam, and steam occupies much more space than liquid water. This expansion creates pressure. If that pressure is contained and directed, it can be used to produce mechanical motion. In a steam engine, chemical energy stored in fuel, usually coal in James Watt's time, is converted into thermal energy through combustion. The heat from burning coal is transferred to water in a boiler. As the water absorbs heat, it changes state from liquid to vapor. This change of state is critical because steam expands rapidly and can exert force on solid surfaces. The purpose of the engine is to convert this force into controlled motion. In Watt's design, steam pressure acts on a piston inside a cylinder. When steam enters the cylinder, it pushes the piston in one direction. When the steam is removed or condensed, pressure drops, and the piston can move back in the opposite direction. This back-and-forth motion is called reciprocating motion. What distinguished Watt's approach was not the basic idea of using steam, but the way he managed heat. Earlier engines lost large amounts of energy by repeatedly heating and cooling the same metal parts. Watt recognized that the efficient use of heat was as important as the generation of heat itself. His engine was designed to keep the main cylinder hot while moving condensation to a different location. This separation reduced wasted energy and made the conversion from heat to motion more efficient. Instead of using most of the fuel simply to reheat metal surfaces, more of the fuel's energy went into producing mechanical work. The steam engine, therefore, represents a system of energy conversion. Fuel right arrow heat right arrow steam pressure right arrow mechanical motion. This chain of transformations is the foundation of later engines, including internal combustion engines and turbines. Watt's contribution was to refine this chain so that less energy was lost along the way. Watt's steam engine consisted of several key components, each with a specific function in the energy conversion process. The boiler was where water was heated to produce steam. It was typically a large metal vessel placed over a fire fueled by coal. The boiler had to be strong enough to contain hot water and steam without bursting. The cylinder was a vertical metal chamber in which the piston moved. It was carefully made to be as smooth and round as possible so that steam would not leak around the piston. The piston fitted closely inside the cylinder and moved up and down as pressure changed. The piston was connected to a beam or rod that transferred motion to external machinery. As steam pushed the piston, this motion could be transmitted to pumps or rotating shafts. The separate condenser was Watt's key innovation. It was a separate chamber connected to the cylinder by a pipe. Steam leaving the cylinder entered the condenser, where it was cooled and turned back into water. This created a vacuum that helped pull the piston downward without cooling the cylinder itself. The valves controlled the flow of steam between the boiler, the cylinder, and the condenser. These valves opened and closed at specific times during each cycle, ensuring that steam entered and exited in the correct sequence. The air pump removed condensed water and unwanted air from the condenser. This maintained the vacuum needed for efficient operation. Together, these parts formed an integrated system. Each component depended on the others. The boiler produced steam. The cylinder and piston converted pressure into motion. The condenser removed steam without wasting heat, and the valves coordinated the entire cycle. Watt's engine was not a single mechanical trick, but a coordinated arrangement of parts designed to manage energy flow. Its success depended on balance. Too much heat caused damage, too little reduced power. Proper timing of steam admission and condensation was essential. The operation of Watt's steam engine followed a repeating cycle. First, coal was burned beneath the boiler, heating the water inside. As the water boiled, steam formed and built up pressure. This steam was directed through a valve into the main cylinder. When steam entered the cylinder, it pushed against the piston, moving it upward or downward depending on the engine's design. This motion was transferred through a connecting rod to a beam or rotating mechanism, producing useful mechanical work. Next, the steam inside the cylinder was allowed to escape into the separate condenser. In the condenser, cold water was applied to the outside of the chamber. This caused the steam to cool and condense back into liquid water. As the steam condensed, its volume decreased dramatically. This created a partial vacuum in the condenser. The lower pressure in the condenser drew more steam out of the cylinder and helped pull the piston back in the opposite direction. Meanwhile, the cylinder itself remained hot because cold water was not sprayed inside it. This meant that when new steam entered the cylinder, it did not lose much heat to the metal walls. The cycle could then begin again with less fuel required. Valves controlled the timing of these actions. Steam admission from the boiler steam release to the condenser removal of condensed water preparation for the next stroke in engines adapted for factories. The piston's back and forth motion was converted into circular motion using gears and linkages. This allowed the engine to drive rotating machines such as looms and mill shafts. The cycle repeated continuously as long as fuel was supplied and the boiler produced steam. Unlike wind or water power, this process could operate day and night, and in almost any location where fuel and water were available. The technical importance of Watt's steam engine lies in its efficiency and adaptability. By reducing fuel consumption, it made steam power economically viable for widespread use. Mines, mills, and factories could afford to operate engines continuously. Watt's design introduced the idea that engines should be analyzed in terms of energy loss as well as energy production. This approach laid the foundation for later studies of thermodynamics, the science of heat and energy. His improvements also standardized the idea of mechanical power. Machines no longer depended on natural forces such as wind or rivers. Power could be generated on demand and applied wherever needed. This changed how factories were designed and where they were built. Later engines refined Watt's ideas rather than replacing them. High-pressure engines, steam turbines, and eventually internal combustion engines all relied on the same basic principle of converting heat into motion. Watt's work showed how to manage this conversion efficiently. The steam engine's influence extended beyond engineering. It reshaped transportation, production, and labor. Railways and steamships relied on similar principles. Entire industries grew around the manufacture and maintenance of engines. From a technical perspective, Watt transformed the steam engine from a wasteful pump into a reliable power source. He did not invent steam power, but he made it practical. His contribution was to integrate scientific understanding of heat with mechanical design. In doing so, Watt established a model for modern engineering. Observe carefully, measure precisely, reduce losses, and improve performance. The steam engine became not just a machine, but a demonstration of how energy could be harnessed systematically. Through these technical principles, Watt's engine became a cornerstone of industrial technology. It showed that controlled energy conversion could drive large-scale production. This insight continues to shape modern machines, making Watt's work a lasting part of engineering history.